Welcome to this second part of this tutorial. The second part is entitled Compilation and Synthesis with Multiple Constraints and Objectives. And my name is Peter Marwedel and I'm with TU Dortmund in Germany. First of all, I have to apologize for not being physically present. I recently had nose cave surgery requiring some recovery period after the surgery, and it would be too risky to have a long distance flight during this recovery period. But I think there's also an advantage resulting from the fact that as a replacement I have recorded this video, because this video could potentially be seen more frequently actually than my presentation at the tutorial. In my tutorial, I'd like to consider cyber-physical systems, which can be defined as follows. Cyber-physical systems are engineered systems that are built from and depend upon the synergy of computational and physical components. This is the definition that was published by the National Science Foundation in the US, for example. So in such a cyber-physical system, we have a physical environment and we have computational components, which we will be calling an embedded system. Now, according to many predictions, cyber-physical systems are a key direction for future IoT systems in combination with a very much related Internet of Things. So we find many different application areas for cyber-physical systems, and therefore we should look very closely at techniques allowing us to design such systems. If we look at those techniques, we find that this tight integration has consequences on requirements, resulting in quite a number of requirements. I will be looking at these requirements during the introduction to the second part of the tutorial. And then later on, I will be discussing how we can take constraints and objectives into account. And we will start with a simple situation, and then we will gradually increase the problems resulting from the consideration of these constraints and objectives. And finally, there will be a conclusion and suggestions for further reading. The first constraint, and also related to that objective that I would like to consider, is the execution time. If we have a tight integration between physics and the computational part, we have to make sure that the computational part will finish its computations within the amount of time that's available. And this leads to the definition of so-called worst-case execution times. They can be defined by looking at execution times of programs. There may be some execution times that are more frequent than others, and among all the different execution times, there are the ones that are the largest feasible execution times and the smallest feasible execution times. Now, for any system of reasonable complexity, unfortunately, we cannot really compute these two times. But we have to be happy with knowing upper or lower bounds for these numbers. And in the particular case of the worst-case execution time, we call this the estimated worst-case execution time. And we require two properties to hold for this estimated worst-case execution time. Number one, it must be a safe estimate, so it should never be less than the largest feasible execution time. And furthermore, this estimate should be tight. That means it should not be too unrealistic. Another constraint that we have to consider is the fact that we only have a limited amount of energy available in case we have a portable system, because then we have to use either a carrying of energy or energy harvesting. There are some extreme cases like these smart boxes that were designed locally at Dortmund at an Institute for Logistics. These are boxes that are aware of their location and their content, and they can perform all computations and communications using as a source of energy the light that's available there in the logistic facilities. I guess you agree that in such a case, the need for energy efficiency is really driving the whole design. Furthermore, a third objective or constraint is resulting also from the tight integration with the physical environment. We have to make sure that our IT system is not causing any harm to the environment, so therefore it must be very reliable. Consequences of this are very frequently underestimated. The order of magnitude of the probability of failures should be very low. For safety critical systems, for example, it's frequently required that this order of failures is less than 10 to the minus 9th per hour. Now this is really a challenge because we could observe that already the failure rates of individual circuits may be orders of magnitude larger than this, and that means we have to use redundancy techniques in order to really design systems with the required reliability. Unfortunately, this problem is only expected to increase in severity in the future because due to shrinking device dimensions, we will observe more and more circuits that will not be performing the function that they were expected to perform. Another constraint and related to that objective is the need to provide safety and security. Safety is impacted by lacking security because if security is not guaranteed, then any attacker can also affect the safety. Now, for cyber-physical systems, we are in many cases requiring that we have connected all the relevant components, and that means that if we have an intruder, he or she can possibly affect the entire system. That means we have to defend ourselves against various types of attacks, against cyber crime, other types of attacks like the Stuxnet attack, cyber terrorism, cyber war, etc. By looking at the corresponding search results from New York Times, you can see that there is right now already a good number of results that are reported in the public newspapers already. One way of providing protection against intruders is to establish local islands. However, such local islands would be in contradiction to the idea of global connectedness, which is so inherent in the term Internet of Things. Now, in many cases, we can also tolerate some deviation from the best possible functional result, in the sense of the result computing as a mathematical function, because in this environment there are many cases where we are tolerating noise anyway. So for example, control loops, they have to be stable despite being exposed to some noise. So if there are occasionally some results that are deviating from the best possible functional result, we can still have a stable control loop. It's similar for audio-video processing. In audio-video processing, we do have noise anyway, so if we have just a little bit of additional noise, that may be acceptable. And then there are results that are by definition already statistical, so if they become inferior by just a few percent, that might still be acceptable. So this means that we can trade off quality against the other objectives. For example, we can reduce the quality just a little and gain something in terms of worst case execution time or the energy consumption. These ideas very naturally lead to the definition of approximate computing, where from my point of view we have to consider also software and not just hardware. Now, for applications, we in many cases do have to classify certain objects. For example, if we have automatically driving car, we might have to classify a certain object as belonging to some class A, but there may be false positives where we assume that it is an object belonging to this class, but it's actually not belonging to that class. And accordingly, there are also true negatives, which is a term referring to the number of times that we have correctly classified one object to belong to some class B. And there are accordingly also false negatives where we classify some object as belonging to class B, but actually it should belong to class A. I'd like to give you one particular example that also helps us to introduce the corresponding quality metrics. Let's consider people that are trying to find amber at some beaches, for example, at the Baltic Ocean. You can sometimes find amber, but the problem there is that there is also white phosphorus, which looks very similar to amber, at least when it's wet. But when this white phosphorus dries, it starts to immediately burn. And if people have put the white phosphorus into their pocket, they will get very serious injuries. So therefore, the false positives should be 0 in that case. That means if you look at the required precision, which is defined as a true positives defined by true positives plus false positives, this means that for this particular application, we are aiming at a precision of 1. In contrast, we can also consider the recall or sensitivity, which is defined as the true positives divided by true positives plus false negatives. We wouldn't care that much about these false negatives there for the case of finding ambers, but in other applications it may be different. If we classify one person to have developed cancer or not, we would like not to have false negatives there. There are 2 additional metrics that we could define, and there is a 5th metric, which is a kind of average between the first 2. Now, overall, we can observe that there is a large set of constraints and objectives, including the 5 objectives that I have already mentioned on my previous slides. And in addition, there are objectives such as thermal objectives, performance, adaptivity, cost, radiation, legal, ethical, usability, etc. And frankly, I have observed that this list has been increasing in length only over time. Now, with so many objectives, there may be the question, how do we actually decide in favor of a particular design point? Taking such decisions is made easier by using the principle of Pareto optimality. A design point in the domain of objectives is said to be a Pareto point if there is no other design point which is superior. There may be other design points that are inferior. And also there may be other design points that are indifferent in the sense that they may be better with respect to one objective and worse with respect to some other objective. Taking all the Pareto points together, we are defining the so-called Pareto front, which in this space of objectives is separating the dominated design points from the area where any existing design point would turn one of the Pareto points into a non-Pareto point. Now, so far we have considered constraints and objectives. Next, I would like to demonstrate the optimization for a single objective. And in this case, I'd like to consider the memory hierarchy for 2 reasons. Reason number 1 is that the memory hierarchy is really an area where we can make a design much more efficient. And number 2, the contributors to this tutorial have jointly written a chapter on memory optimizations in a forthcoming book on hardware-software co-design, and this chapter is one motivation for this tutorial. So therefore, let's look at memories, and I would like to start by first of all looking at memory hierarchies. Some people might believe that memory hierarchies are a rather recent ideas, but this is not consistent with history, because looking at this citation, you may be surprised to see that memory hierarchies were already introduced more than 60 years ago. Burks, Goldstein, and von Neumann wrote back in 1946. Ideally, one would desire an indefinitely large memory capacity such that any particular word would be immediately available, and especially in a time which is shorter than the operation time of a fast electronic multiplier. It does not seem possible physically to achieve such a capacity. We are therefore forced to recognize the possibility of constructing a hierarchy of memories, each of which has a greater capacity than the preceding, but which is less quickly accessible. As a particular case, I'd like to consider one level there in the memory hierarchy, which is called the Scratchpad memory, which is a small memory but which is very fast. Scratchpad memories are memories that are small, physically separate memories mapped into the address space, and they are selected if we use an appropriate address within a certain range of addresses. So typically in the address space we have certain addresses that are used for Scratchpad memories. So in contrast to caches, we don't need any tags there. Scratchpad memories have become very popular because they are so fast, because they are so small. For the same reason, they are also energy efficient. And most of the time we know whether or not at runtime an object will be there in the Scratchpad memory, so therefore they are also timing predictable. Scratchpad memories have been introduced many years ago. And what I'm showing here is one of the first dies that contains such a Scratchpad memory. It's the ARM7 TDMI, which contains next to the processor some RAM area, which is implementing a Scratchpad memory. Now, for Scratchpad memories, we require allocation, and I think I would like to distinguish between three different dimensions here. It's first of all the type of object movement, second it's the type of the architecture, and third it's the objective that we are considering there. And for the type of object movement, I'm considering non-overlaying approaches, or sometimes called static approaches, compile time controlled approaches, compile time controlled overlaying approaches, and completely dynamic approaches. And we can also consider different objects, we can consider different types of architectures and different objectives. In order to get started, I'd like to start with one of the first approaches that we were working on. We at Dortmund were considering objects that might correspond to, let's say, for loops in the code, or might correspond to while loops in the code. And also we considered global variables as such objects. Now the overall optimization problem for non-overlaying allocation can be phrased as follows. For each of these objects there is a certain gain if we move that object there into the little Scratchpad memory. And for each of these objects we also have a particular size. Then the overall goal is to maximize the gain while respecting the size constraint. Now obviously this phrasing of the problem means that the problem is in the form of a knapsack problem, and therefore knapsack algorithms can be used to solve the problem. As another option, we can be used integer linear programming. Now as a result, you can see on the slide that we can have substantial savings in terms of the energy consumption. How much we are actually saving depends a little bit on the details of the memory. If we have a partitioned memory, then we can save more than for the case of a non-partitioned memory, because in this way we can easily adapt to the size of the so-called working set. So if the memory becomes much larger than the working set, then we have also an increased energy consumption, and the saving will be decreased. Now this is a presentation of just the optimization of the allocation of objects, but recently we are using more and more multicores, and we believe that therefore it's necessary to integrate such an allocation into the mapping of threads to processors. Therefore, students at my group have extended the DOL processor mapping tool that is available from ETH Zurich in such a way that we are also considering the mapping to the memory system. And as an example, we have been considering a multi-core system involving four homogeneous architectures, four homogeneous processes. And we can show by how much we can reduce the energy consumption by using integer linear programming for maximizing the energy saving there. And you can see that for the different applications, we can reduce the energy consumption by 40 to 50%. And as a byproduct, we also have a reduction of the execution time. Now, this was still static allocation. More recently, there has been more and more emphasis on dynamic applications. In this case, I'm considering a scenario where we don't even know the applications at compile time. So therefore, decisions have to be taken at runtime. This can be done by a Scratchpad memory manager, which has to make sure that before we start a particular application, the required objects are there in the Scratchpad memory, and then before we switch to the execution of some other application, we have to make sure that the corresponding objects are again there in the Scratchpad memory. And when we switch to the execution of a third application or thread, we have to make sure that their objects are also there in the Scratchpad memory. And now this continues on during the execution of these applications. Now this is a pretty dynamic scenario. Now with all these approaches, we can think about how much we can actually reduce our objective, and I'd like to show you an upper bound for the reduction of objectives such as runtime or energy. For this purpose, let's consider two memory layers, and in this case, as objectives, I'm considering the access times, and we assume that between the access times there is a certain ratio. Furthermore, let's assume that we can replace a fraction p of references to the larger memory by references to the smaller memory. And then we can consider the relative saving, and we find that the relative saving is p minus p over s. Now suppose that we are able to make s very large, and these days s can actually be 2 orders of magnitude. Then this means that the second term more or less vanishes, and it's the p which is defining the relative saving. Also, if we look at the speed up, we can rephrase the equation in such a way that we have p over s here as a first term. And again, if s becomes very large, this term will almost vanish, and it's 1 minus p, which is important. So this is actually very similar to Amdahl's law. It also corresponds to what people consider for caches, but unfortunately in many cases this bound is forgotten for Scratchpad memories. Because in practice it means that if we are not replacing, say, code, or if we are not replacing local variables, then this fraction p will be very much constrained, and as a result the feasible speed up is also very much limited. So with this remark about something that is frequently forgotten in papers on Scratchpad memories, I'd like to finish this first half of this tutorial, and I'd like to check if there are any questions for this first half. Otherwise, I would like to ask those operating the laptop to start the second video that was recorded. Thank you very much.